different, fascinating topics. The first is an intersection I never would have believed between neural networks and ring theory. And so Virgil Barnard will tell us all about that.
Hello, I'm Virgil Barnard, graduate student, instructor, faculty. A little bit about me, I've got my bachelor's in mathematics, came over here to get my PhD in computer science. It's been a long process adapting, getting used to all the language, especially object-oriented language patterns. But I've been committed to it, and one of my principles is that I wanted to be able to implement ideas, not just have them in an abstract form. So this project was kind of geared in that direction. I hoped to be able to actually implement concepts. And actually, the notion of a neural ring had not occurred to me until this last Sunday while trying to work on this project for a different direction, which was just to define relations in general. And now I'm just kind of throwing a hook on it with the concept of a ring. But does have a nice ring too. Thank you. So an overview of the talk. I'll first give some incentives for bridging the gap between concepts in mathematics and computer science, but mostly I'm just going to quote two authors that recently wrote papers that are complaining about the difference between, or the segregation basically between mathematicians and software developers, computer scientists. Then I'll talk about sets and binary relations. Talk about binary relations as transformations. I'll argue that elements, like in the context of a set, are really just objects, like in any object in a language, an object-oriented language. Talk about object serialization. It'll be our method for feature extraction. Rings, just give a quick, really a brief definition of that, a conventional definition. Define a neural ring, which obviously is just a coined term for this project, and system description for developing a neural ring, and then I'll demonstrate it in Python, which is a new language. Like I just learned playing with Python a couple weeks ago. But so mathematicians are able, through the use of Java or C++, textualize mathematical abstractions in software. Equally, computer scientists are able to explore fundamental concepts in mathematical constructs through easily accessible and natural medium of expression. I don't like reading completely paragraphs from the slide, but it seems important to just include that statement that mathematicians are able to contextualize the abstractions more concretely, and computer scientists can explore the abstractions, vice versa, so it's an intermingling of two different fields. Another author refers to there being a software crisis between pure mathematics and computer scientists. They also claim that it's astonishingly simple to implement complex mathematical structures in an object-oriented environment. So that paradigm of object-oriented language patterns is extremely powerful and expressive in the context of abstract thought and mathematics. And the primary problem is bridging the gap between the two worlds, mathematicians and the expertise of software developers. That paper, he was mostly referring to design principles in object-oriented. The object-oriented paradigm, because a lot of mathematicians aren't aware of those rules, and they'll develop huge programs without any reuse of code or functionality. So he was trying to stretch that boundary. This project is intended to teach basic concepts in mathematics and computer science pertaining to sets and relations, rings, object-oriented programming, and neural networks. So it's just bringing in all those concepts together in one program. This project also demonstrates how to build a basic user interface, which to me was something that I had never done. So I took this opportunity to try and actually create my own and understand that process. Loading set objects, which I construct the set class, and then this user interface will load the set objects, do build relations, and animating images, which surprisingly took a day to figure out how to make it save the file and load it continuously. Simple thing. The applications only tend to be educational and experimental. So the big question, why? So I'll point to that right now. That's what this is for. The second topic, sets and binary relations. So the term binary is overused. Here I just mean two, taking a map from one set to another. There's two sets involved. Sets are collections of abstract objects. You take a one like that, call them elements. X and Y are two sets. A relation from X to Y is typically described as a set of ordered pairs. With the first component from elements of X and the second component from elements of Y. That's the conventional definition. If you were to Google it or Wikipedia, that's going to be in the first paragraph. It's a set of ordered pairs, binary relation. But they're more than just ordered pairs. It depends on context, especially in computer science. We are talking about transformations in a lot of cases, concrete transformations. Sometimes the ordered pairs aren't known ahead of time, maybe we're discovering them. So I am saying that binary relations can also be transformations. It can be a set of instructions for transforming elements in one set to elements of another. In the context of computer science, you can think of a relation object R as being able to take an ordered pair of elements as input and return true or false whether or not that ordered pair is in that relation. And it might discover that based on some set of instructions for transforming the first element to the second element. And there might be overridden rules for what a quality is. Maybe after transforming X, I get something that looks like Y enough. I predefine the quality and I return true. There's more variability in the definition. And then I'm proposing that there's two main types of transformations for this project, syntactic and physical. And the reason I'm dividing those transformations in these two sections is because syntactic, I mean that it requires domain knowledge as far as transformation on the objects. It can be a lookup table, it can be algebraic methods that are known on those objects. There's a bunch of different lists of things you can imagine. Some data tables, it could be, and we're just looking for synonyms in the titles. But physical, I'm implying that it's at the lowest granularity. We have no knowledge about what these objects are, how to describe transformations on them. Physical, I mean, we're going to actually construct transformations on the representations in memory. And that kind of pushes us to the question, what are physical representations? In computer science, we're concerned with most representations that can be interpreted by a processor. So in particular, sequences of electric pulses received over an elapsed time. We freeze. Now, I'm just using that term loosely. Obviously, there's a lot involved in thresholding the electric pulses and deciding which one is a 1 or a 0, things like this. But we freeze the representation of the sequences as an array of zeros and ones. Remember, we call that a bit sequence, or bits. And the coin term typically used in computer science is a chunk of 8 is a byte. So I'm saying explicitly this is a temporary definition because really it's 8 doesn't make a difference. We could have partitioned them into 10, 12, whatever, but for now, 8 is convenient because that sits nicely inside of a lot of the currently implemented methods for object serialization, which is defined as sequences of bytes. So element serialization. So now I'm going to transition from the context of sets, being collections of abstract objects we call elements, move back into saying that they're objects in general. We refer to the process of converting elements into their physical representation as object serialization. We use the term object because we're borrowing conventional concepts from computer science. The important aspect of this process is that it can be undone. So there's several different, I'm not going to click on that link, there's JavaScript object notation, JSON, which is currently used. There's also an XML. These are widely used conventions for serializing objects. In Python, we use something called pickling. What is most important is that you have a method for taking an object in memory, current instance of the class, and then translating it into a sequence of bytes. And that can be undone. Whatever format you choose, obviously that will be just fine as long as it's consistent. Perfect. that is our method of feature extraction. Okay, so that's actually going to happen before any neural net is evaluating your object or anything like that. So that's wrapped outside the activation of the neural network. And I'll go into that soon. Real quick, rings. This is supposed to be intended for anybody who has no knowledge of rings. A ring consists of a set we talked about, but two binary operations or relations that generalize the arithmetic operations of addition and multiplication. For our purpose, that's enough to say what a ring is, and here's an example of the ring C mod 3, which many of you will have seen. And there's our addition table. We can define it like this: 0 plus 0 is 0, 0 plus 1, 1 equals 2, 0 and 1 mod 3, and multiplication table. And that's conventionally how you would express that ring through tables. But we can define addition and multiplication as a mapping from all ordered pairs of 0, 1, 2 into that set using a relation matrix, right? So this is more of an explicit mapping. I'm actually saying that the ordered pair 0, 0 maps to 0 under addition rule, and the ordered pair 0, 1 maps to 1 under this addition rule. It's more explicit. These are objects. These aren't just ordered pairs. I'm going to be mapping using neural networks to map that actual ordered pair object into number 1 or 0. And try to remember that pattern. So I use that later on because we're going to make a set that's isomorphic to Z mod 3 in the same way. Neural ring definition. So neural ring inherits the conventional definition previously stated, but implements it by supposing two binary operations are neural nets. They operate on physical representations, as I've defined what a physical representation is. Neural nets, we're all using machine learning. I'm not going to go into the details of this talk. I think that that portion, talking about machine learning neural networks, gets talked about way too much. But for the purpose of this, I'll just say that you should know that it exists, that there's general models that can map arbitrary mappings, so that we can create arbitrary mappings from sequences of bytes to sequences of bytes, or physical representations to physical representations. We'll use the one hidden layer sigmoid gate transfer function with back propagation as our learning strategy. This is like the typical one you learned about initially in the machine learning course. System description. So this just outlines the process of creating a neural ring. Given a finite set of objects, within of them there, we form the cross product of those two. So we have to form all ordered pairs. I'm going to set that as equal to the set X. Form the serialized representations of X and Y, all those S sub X and S sub Y. So we're mapping those through our object serialization process, but that's also including padding. So I'm going to look for the longest length representation in set S sub X, and then I'm going to pad all the other ones with 0 bytes. So they all have the same length. The reason why is because we're going to be mapping this into a neural network and throw an error if they don't have the right length. So, we're going to interpret every byte as an integer from the range 0 to 8 minus 1. Obviously, that means that you have to cast byte as an int in the program, and we're going to have those methods available on that representation. We're going to construct two neural nets, call them add net and null net, that map the elements of S sub X to the elements of S sub Y according to the isomorphic qualities that we wanted. Really, we're just constructing two groups that together make a ring. I didn't say what before we started. Include rounding to the nearest integer of the output byte. We don't want to keep training until machine precision is reached. We'll just round to the nearest integer, and if it hits the right one, we're done. We don't have to keep training. And we're not worried about partitioning data sets or anything like that. We're just constructing this network to actually fit the mapping that we want. So we train until it's right. And Python, this is the real quick thing. I'm just saying that we can go into the class descriptions. Like we'll define a class later on, and go in and I can redefine what the addition and multiplication operators are to use my neural nets first forming the ordered pair object. So when I do call this object plus this object, what will happen is the ordered pair will be formed with parentheses and everything. That will be serialized, and that will be sent to the neural network, which is prepared to already map all ordered pairs with parentheses to those objects correctly. And over here, this is just quickly saying what evaluation is. This evaluate takes that ordered pair the neural network object that we'll create and evaluates with respect. And what's happening behind the scenes is a series of assignments for serialize, turning bytes into ends, add according to what the max was observed in that application, and then activating that on that, round each position, each byte, integer, and then take absolute value, because sometimes I get a -0 in that and deserialize. And you could also say inst bytes there, but I don't need to do that step in this particular context. It's Python.
There's no guarantee that when you deserialize, you get one of the original objects. Is there? You might get something.
If you've trained everything properly, yes.
Okay.
If you've trained it right.
All right.
But yeah, but it is interesting to ask, like, what happens when I now evaluate something that I haven't trained on? Will I get an object? It doesn't make sense. So I'm using Jupyter Notebook to run Python code. Real quick, these are the libraries that I used.
Can you tell us what Jupyter Notebook is?
It's just a web-based application for running Python. So it's just convenient platform for programming in Python. We have the Tkinter, which is actually used for developing user interfaces. Feed-forward network, all those four are used for the neural nets. Pickle is our serialization library. NumPy for multi-dimensional array management. Matplotlib for displaying images, and so are image in the image. Time to put a pause step inside the routine so you can actually see the training occur. So yeah, let's just pass that. So first off, I'm going to define set class. Now, the domain logic that's involved in my set class implementation isn't necessarily the best way to do it or anything, but it's enough for this project. I'm initializing every set with a name, and it has an array, an empty array initially of elements, and I'm automatically removing duplicates if it was initialized with duplicates. And I'm defining equality on sets to be named. None of this really matters at this point in this project, though. So we have a set class. I can add elements, I can take cardinality, and I can clear the elements in that set. These are some functions that are used globally. I need padding, this pad function, which takes an array and an integer and pads integers or zeros. I need to convert bytes to ends, and I need inst bytes. And there might be current libraries to do that in Python. I didn't bother to look, just wanted it done.
Looks like there's a library for sets.
There is actually a library for sets, and I should mention that. That didn't come out until Python 3 as a default library, so it's relatively recent. But I also wanted to make sure I had more control over how the sets worked for the purpose of this. So I call this object, this class, core mutation device. This is our actual user interface for constructing relations, and I'll go ahead and get into that. And I'll jump back into the code of it in a second. Oh, so I initialized the class there. All right, first off, I'm going to create an arbitrary set. Now this set has the name set, and it consists of the character A, number 3, and the order pair 1, 2. So just as an example, these are arbitrary objects in this set. I'm initializing my teleportation device as no parent. I'm going to be mapping elements of Y back to Y. I'm naming this net, and I'm giving it a title of communication device. And this is where it loads. What this is it's going through and it's actually going to get the string representation of the elements, relation matrix, I can construct the relation. I can click and see what the elements are in the relation, the ordered pairs, and take them away. Simple stuff like that. This is the identity relation. I'm going to map A to A, 3 to 3, 1 to 1 to 1 to. And then I'm going to say construct relation. And you can see the actual, if this had coefficients in the input layer of the neural network, and the first square root of n are the ones that are mapping from the first input byte to all the in sigmoid gates inside of the neural network. So this is the input layer weights, these are the output layer weights. It took 37 iterations to train it. It stopped once the rounding worked and we got the correct map. So to show that, I'll just evaluate 3 at 3, and I see that it actually maps to 3. Now, I'll go into the details of what evaluate is again in a second, but let's just real quick make a different one so that you see that you can also make A map into something else. Now, 3 maps into the character A. Now, those objects didn't have any methods or attributes or cool stuff that we could like play with, right? We'll get into that. So first I'll just say, recall the definition of evaluate was. In the middle, I'm first taking the element and I'm pickling it. So right here, I'm going to pickle 3. You can see it, and I've already done all this, right? But here's the byte string of 3 after being serialized. And then we turn it into int. And then I pad it with the maximum that was determined during the creation of that relation with respect to all the other elements that I was mapping. Turns out that that was the max length. Now this is what the output of the network actually was. Machine precision float values going around. And so we actually we're still in float, so I convert, first I'm taking absolute value, then I'm doing an as type unit, so I'm turning these into unsigned integers. Then I'm doing pickled uploads. So yeah, maps A. So 3 maps A, we solved it. All right, now we're going to construct a ring. And so now first I'm forming all ordered pairs, and we're going to do add net. We're going to create the addition form. And if I go back to this real quick, show you what the pattern was we determined earlier, just to recall. I've basically patterned all that stuff similar to this, where the character A is at the beginning. I'm going to be mapping it into the same. So A is 0 is what I'm saying. A is 0, 0 plus 3 is, 0 plus 1 is 1, so on and so on. I'm doing this quickly because I've done it many times. I know that that's the addition mapping for ordered pairs. I'm pretending that A is 0, 3 is 1, and ordered pair 1, 2 is 2. Okay. This takes a little bit longer.
That's because of the delay loop.
I wasn't printing the image every single step either. It takes a lot more time to construct the image than this training. So 858 iterations, and so we have the so yes, so I can add over my other
0 plus 0 is 0.
0 plus 0 is 0. 0 plus 3 is 3. Tested, and or 0 plus 1, sorry, and 0 or 1 plus 1 is 2.
Could you add A and B?
I never trained it to add the character B. Is that
What
you-
happens if you try it now?
Okay, let's try it. Jason can break the system. Ah. It does not know how to unpick that, I'm sure.
Okay, just bring that pickle.
Yeah.
All right.
Let's define our own classes. I'm going to transform dogs into cats. So I'm going to first just say that I'm going to create a pet class. subclass pet. It's gonna modify speak to bark, and cat's gonna modify speak to meow. And I'm creating these dogs as cats. I know I'm running out of time. So bark does bark, mittens does meow. Just confirming that before I send them through the training implementation device, they work. And I'm creating sets. I'm going to create a set called dog and a set called cats. And now I'm turning off image generation because it takes way too long. And I'm going to construct a net called dog, cat, net. And we can map these however we want. I can map Roo to Scratchy, I can map Maple to Princess, and Iggy to Mittens. So we'll do Roo to Scratchy. Let's see, it's Roo's. It's already done. So now I'm going to see where Roo goes. It's Scratchy, right? So I can just still call the methods on it, all that good stuff, right? Does meow. Okay. All right. So now I'm going to make an isomorphic set with the dogs with Zmod 3. But I'm also going to first do the modifications to the operators, add and multiply like I was talking about, so that when I actually call addition on them, it's going to do the isomorphic mapping. I'm going to reinitialize my dogs, and I'm going to create first all the dog pairs. And now I'm going to construct my add net under the same pattern as we were seeing earlier. Where I'm presenting Roo is 0, Maple is 1, and Iggy is 2.
This is the addition relation.
Yes, sir. So going for D4 iterations. And I'm going to add Roo plus. So Roo is 0. Wait, I have it up here. Roo is 0, Maple 1, Iggy 2. And I do get Roo plus Iggy is Iggy. Maple times Iggy, which is 1 times 2.
You ever trained Walnut?
Oh, I didn't train them on that. Thank you. Sorry. Just train that moment. And I know that it's 0 times 0, 0 times 1, 0. So it's the first 5. And then it's these 2 and these 2. And we can go back and look at my PowerPoint. And it's the same pattern. I've structured it also. Iterations. Now let's make sure that Maple times Iggy or 1 times 2 is still 2. Oh, we can do multiple operators, and I can still ask what type of pet it is. Maple is mixed breed, as I defined Maple earlier. All right, so now I've actually turned objects into a set of objects into an isomorphic set. Any questions? That's pretty much the end of my presentation. I don't know how I went on.
You're fine, you got 1 minute for questions.
Great. So, yeah, I'll just bring up real quick the user interface. Obviously, was my biggest hurdle for me in this project. Yeah, anyway, if anybody wants to code or if they want to play with